In this video, we will talk about the Euler's method. It is one of the numerical methods in differential equation that is used to estimate a particular solution of a first-order differential equation. So this is quite well-known method, and actually it's made its way to the Hollywood. Let's watch it.
Is when the capsule moves from an elliptical orbit to a parabolic orbit. There's no mathematical formula for that. We can calculate launch and landing, but without this conversion, the capsule stays in orbit. We can't bring it back home.
Maybe we've been thinking about this all wrong.
How's that?
Maybe it's not new math at all.
It could be old math. Something that looks at the problem numerically and not theoretically. Math is always dependable.
For you, it is.
Euler's method.
Euler's method.
Yes.
That's ancient.
But it works. It works numerically.
That's it.
Let's type it up.
So Euler's method, why do we care? Well, so far we learned how to solve some of the differential equation explicitly, right? Meaning that we can find the solution to a differential equations using any of the elementary functions, such as polynomial functions, trigonometry function, exponential functions, or logarithmic functions, so on and so forth. But very quite often that a given differential equation cannot be solved explicitly. An example can be, let's look at this differential equation dy over dt equals to t squared plus y squared. I guess you can try to solve this differential equation by trying to separate it t and y on both sides. We couldn't do it. Or you can try to use the integrating factors. It couldn't do it because you have y squared here, which doesn't make it a linear differential equations. So what can we do? We know that this differential equation is not linear because of this fact. And then the solution to this differential equation cannot be written down using any of the elementary functions. However, the existence and the uniqueness theorems tell us that a solution does exist. If you have a solution does exist, and is in fact unique solutions. Okay. Well, why? How do we know that? So again, using the existence and unique theorem, we can show that a solution to this differential equation exists and unique if you have an initial value. Okay. If I call this functions as, f of t and y, okay. And then I would know that the function f of t and y here is continuous everywhere, from negative infinity to positive infinity. So that means and then the partial derivative in terms of y of the function f of t and y is equals to 2y. So it's also continuous on everywhere, right? Negative infinity to positive infinity. So that means there exists, so from this fact, that means there exists a solutions. There exists a solution. Okay, and then from this fact right here, that means there is a unique solutions. Exist a unique solutions. That means if you give any a initial value to this differential equations, you guarantee to find a unique solution to that IVP. Okay. If you have an IV, let's say t0 equals y0, f of t0 equals y0, then you have an IVP problem, then you guarantee to have a unique solution. Okay. But how can we find the solutions? How can we estimate a solution, let's say? Well, one way we can try to solve this is we can use numerical method, a numerical method to solve this differential equations. So a numerical method will give you an estimate solution, not an exact solution, but an estimations of the solutions. And then the idea behind Euler's methods is to use the tangent line approximations. It's a tangent line approximations is a line that we use derivative and a point in order to approximate a point. This is one concept that we learn in Calculus 1. Okay. So if we recall from Calculus 1, we know that the tangent line approximation is given using this formula right here. You want to estimate y of t, you can use a t0 and y0, right? And then once you find the derivative of the function y in terms of t0, and then you multiply, and this is going to give you the slope of the line, and multiply by the distance between the t and the t0. So this is just the point slope formula of a line. And if we use the derivative to find the slope of the line, then it's called the tangent line approximation to approximate this point right here. All right. Now we can try to develop Euler's idea. Okay. Let's say we have a generic differential equations y prime equals to the functions in terms of f, in terms of t and y. F is a function in terms of t and y, and then f of t and y is the derivative of y. And we given an initial value. The value of y when t equals 0 is y0. So we have an IVP. And the idea is, can we estimate a value? Let's say estimate y of 3. Okay. Given t0 is 1, and then y0 given f of 1 is 2. Y of 1 is 2. So y of 1 is 2 means 2 is the y0 and 1 is t0. Can you estimate y of 3? Right. Again, this is a generic function. Well, let's graph it. So I have, this is t and this is y, right? And I have t0 is 1, 0, 1, 2, 3. And I have y0 is 2. This is t0 equals to 1. Okay, so now I want to use the point t0, y0 here in order to estimate the next point on the solution curve. Just imagine I have a solution curve somehow, right? But I want to start from this point, this initial point, go to the next step. And I define the width of each step is gonna be 0.5. So I define set, I call it delta t. Delta t is a fixed distance between the two consecutive steps in my estimation. So delta t equals to 0.5. What does it mean? That means my next step is gonna be at 1.5. Okay, because from here to here is 0.5, and I call this t1. Okay, so how can I estimate y1? The y value corresponding to t1. I'm going to use my tangent line. I'm going to use this point right here. So the point y2, if I know it correctly, y2 equals to y1, right? I'm using this point right here. Now let's say it should be y1 and y0. y1, which is the points that I'm trying to step up from y0, equal to y0 plus y prime at t0 times t minus t0. I'm just using the line approximation, a tangent line approximation formula here. Now I'm going to define what is y0. I know y0 is 2. What is y prime when t at t0? I know that if I plug t0 in here, and then I have y0 in here, then I have f at t0, y0. Okay. Keep in mind, y prime is the function f of t, and y is given. It's your differential equation that you're looking at right now. So that's why you can use the tangent line approximation, because you have the information about the slope of the solutions at a point t. And then t minus t0, which I already assigned, is going to be 0.5. Okay, so I found my y1. I have all the information here. Then I just plug it into this equation to find y1. So go to the next step. y1 is here. Now, how can you go to the next step to, let's say, y2? So my next step will be estimating the y value when t equals to 2. This is y2. I'm using the same formula. Now, let's see, I'm gonna delete this. You know what I'm gonna do, right? I'm going to y2 equals y1, because I have to use this point right here, y prime of t1, y1, right, t2 minus t1. And then here, y2 at this point, y1 at this point is the point that I already found. It's not 2 anymore. It should be y1. And y1, let me assign, this is going to be 2.5. So this is 2.5 plus f of ty, t1, y1, because again, you're using this point to estimate the next step. Multiply by 0.5. So 0.5 here will stay the same at every single step that we are making. Okay. So then again, I just go to the next step. And then I'm using the same formula, the same process to go to the step after it right here. And then the last step is going to be the point here. So by repeating this process over and over again using the right point, the right previous point, I can estimate the value of y when t equals to 3. Right here. Okay. So it's very, very simple. As long as you understand the process, as long as you remember the tangent line approximation formula, then as long as you plug your information in each step correctly, you'll be able to estimate any of the particular solution to any first order IVP problem. So let's consider again the initial problem that we ran into, right? Equals t squared plus y squared. And let's say I have an initial value y0 equals to 1. So I want to estimate y1. So before you can, you know that you can do this, but you have to decide what is your step width. So the step width is, let's say I decide, so I will go from 0 to 1, and then maybe I want to do like 5 steps. So I decide my step width is going to be 1 minus 0 divided by 5. So it's going to be 0.2. So I know that my step width is 0.2. That means I start at 0 and I go to 0.2 and 0.4 and so on and so forth. Okay, let's try it. So I have t, I have y. I have my initial value as 0 and 1. So this is y0. Okay, and I know that my step width is 0.2. I know my destination is 1. I need to know what is y of 1. And then, so I'm gonna 1, 4, 6a. So I divide the interval from 0 to 1 into 5 equal parts. So step 1, start at the original point, start at the initial value, 0 and 1. And then you go to the next step, 0.2. You have to use the formula again. Remember, if you want to find y1, you use y0 plus y prime of t0, t1 minus t0. Okay, so y0 here is 1, and y prime at t0 is gonna be, so if you plug 0 into t and 1 into 1, the y prime will be just 1. And the difference between the two steps is 0.2. So that means the next step, y1 will be 1.2. Okay. y1 equals 1.2. Let's stretch this out a little bit. Say y0 equals 1. 1's right here. And then y1 should be 1.2. It's over here, right? So this is where your next step is. So you start from here, and your next step is right here. Okay, and then you keep finding what is y2, y3, y4, and y5, and so on and so forth. Well, I just show it over here how to find the equation of the first line. The equation of this line is actually this equation here. So you will have y1 equals to y0 plus y prime of t0, right? t1 minus t0. And then you have y0 is, in this case, is 1. And y prime is t squared. And I found that it's just going to be just 1. And t0 is 0. So then the t1 here is just t, right? So again, this is the equation, not the formula of the y. So then you have just t. And if you plug t1 and t0, you will find that y1 equals to, plug this equals to 0.2, 1.2. Okay, how about the second line? So for the second line, you need to know that y2 equals to y1 plus y prime of t0, t2 minus t1. Okay, now we know t2. Now we know y1, which is 1.2, and we have to plug t1. Should be t1. So you use this point, t1 and y1, in order to estimate y2. So you plug t1 is 0.2 and y1 is 1.2, then you have to find the formula. So the dy over dt equals t squared plus y squared. Now t equals to 0.2, so 0.2 squared plus y squared, which is 1.2, is 1.2 squared. Okay, so then this is the formula. This is the equation. And then if you plug the information into this equation, then you will have your the point y2. Let's calculate another one here. So you have 0.2 squared plus 1.2 squared is 1.48. And again, t2 minus t1 here is always just 0.2, as we already defined. So what is y2? So it's going to be 1.496. Okay. So y2 is 1.496. So that means when t equals to 0.4, y2, so about 1.5. So this is the value of y2 at t equals to 0.04. Okay. Again, we use the previous point to estimate the next point. What about the equation of the third line? In this case, I'm just going to write down the equation, right? The third line where y2, remember what, using the previous point plus y prime of t2, and again t3 minus t2. The fourth one, y4 equals to y3 plus y prime as t3 and t4 minus t3. And the fifth line, which is the line that will help us find the estimation of y of 1, which is y4 equals y plus y prime of t4, t5 minus t4. Okay, as we already know, t1 is going to be 0.2, t2 is 0.4, t3 0.6, t4 0.8, and t5 is going to be is 1. Once we define all the equations for all the lines, tangent lines, we can just plug in the informations in order to estimate the point when t equals to 1. All right. Now, to summarize the Euler's method, again, we can, to obtain a numerical solutions to differential equations with initial value on an interval between t0 and t star. We divide the interval into equal pieces of step size, h, then starting with n, big N equal to 0. Okay, and then as you already noticed that we use the tangent line approximation to come up with the next point, the value of the next point. And if the point y sub n plus 1 equal to y sub n plus h, which is the step size, multiplied by the functions where t sub n and y sub n. And these functions here, again, it's just the derivative of the y. And as you know that, t sub n equal to t0 plus big N times h. Again, h is the step size or the step width that we mentioned before. N is the number of intervals, the number of steps that you want to take in order to estimate a value. And t0 is just the value of the initial point. Okay, so it's easier to use the Euler's method in order to estimate a value by populating a table. Okay, so this is an example of a table that we can use. I have big N, which is the steps, T of N, right, which is the value of T at each step. And this is the estimation Y of N, Y sub N. And this column here is just an estimations, it's the calculations of the derivative at the step N. And because our differential equation here is T times Y, that means the derivative, and this is just the function f of T and Y. So that means in order to find the derivative of the equation of the line, we need to take T times Y. Okay, and we know that we want to have a step size of 0.2, and we know that the initial values is y of 0 equals to 1. That means t0 is 0, and y0 is 1. And then h is the step size is 0.2. So we have all those informations. And now we just need to populate a table. And in order to come up with the estimation yn, we need to use this formula here. And then in this table, you can see that this is where you find the derivative, right, of the line. And this is the derivative multiplied by the step size right here. And if you add to the y sub n, then you will have the value y sub n plus 1. All right, so let's start it. I start with 0 because t0 equal to 0, and I know that y0 is to 1. Then plug in this value. My next value y1 will be 1 plus 0. All right, y sub n plus f sub n times h, which is going to be plus f sub n times h is going to be y sub n plus 1. Okay, so y1 this is y1 equals to 1 because 1 plus 0 is 1. And then I just keep calculating these informations. And then at the end, I know, okay, so y2 here is going to be 1 plus 0.04. Okay. And then y3 here will be just 1.04 plus 0.0832. And y4 here is going to be 1.1232 plus 0.134784. And then I'll come up with my y5. So y5 is going to be, this is the value that I want to estimate. So the y of 1. Remember, t equals to 1 and y of 1 is 1.45921, so on and so forth, right? So this is the number that I came up with using the Euler's method. I use the step size of 0.02, and I use this formula here in order to come up with the tangent line approximation, so then I know what is my next step in my approximations. And then this is my destinations here, right? I estimate that the y of the y value when t equals to 1 is going to be 1.4592174. Well, luckily, this differential equation is simple enough, or this IVP is simple enough that I can find the real solution, the explicit solution for this differential equation, which is y equals to e to the t squared over 2. So this is the explicit solutions, the real solutions, right, of this differential equation. And using these solutions here, I can calculate the exact solution, exact value of the function at each point of t. So when t equals to 0, y0 equals to 1. When t equals to 0.2, y of 0.2 is 1.02. When t equals to 0.4, y of t is 1.08, and so on and so forth. So then I know that the exact value when t equals to 1 is 1.64872. So the exact value is 1.648, and the estimated value is 1.459. They're not the same, they're a bit different, but they're not so much different, right? So the difference is about less than 0.2 is the error of this estimation, which is not great, but it's not that bad. So without this Euler's method, I have no idea how can I calculate or how can I estimate the function value when t equals to 1. But now I have some idea, it's close to 1.459. All right, and then this is the direction field of this differential equation, and you can see that when this is the initial value, and this is the solution curve of this differential equations, e to the t squared over 2, and then as you can see that, so we start from here and we want to estimate at this point right here. This is where we want to estimate it. And then we use Euler method, which just goes slowly up, you know, and then up and up and up and so on and so forth. Okay, so the estimation value is not the same as the real value, but it's very, very, very close. So this is the real value, and this is the estimated value. All right. Now, let's try to decrease what happens. Let's ask a question. What happens when we decrease the step size? Let's say h equals to 0.2 0.01 or h equal to 0.001 and so on and so forth. What will happen if we decrease it? Again, if you decrease the step size, the smaller the step size is, the more calculation, the more number of steps that you have to take. So more calculation that you have to make, but maybe you will have a better estimation. So this is the program, Python program that helps me to calculate the value of the function of the solution at each step. Also to calculate the value of the solution at the final step. So for an example, in this case, I use delta here is the step size. So I use a step size of 0.2, and as we already manually calculated it, the estimated value is 1.49459, and the true value or the real value is always 1.4687. Okay, now if I want to decrease the step size, let's say 0.02, okay, and then I run it. You can see that the curve is a little smoother, right? And the estimated value is 1.627, which is very, very, very close to the true values, which is 1.648. Again, I just decreased the step size from 0.2 to 0.02. Now, if I add another 0 in here, and I run it, see what happened. You see the curve is much more smoothly, right? Smoother. And also the estimated value is very, very close to the true value, which is only 0.002 difference. So as you can see that the smaller the step size, the better of the estimation that we're gonna get. Now, here's a few things that you want to be aware of when doing numerical approximation. Again, Euler's method is just one of the numerical methods that you can use in order to estimate a function value. Okay, so one thing you keep in mind is you will not get an exact solution, and that's fine, right? It's always an approximate solutions. So then there's always error. Even though, remember, even though when we decrease the step size to 0.002, we haven't got to the exact solution, which is the estimated solution close, but not the same, so we have error. So the question is you have to ask is whether the approximate answers that you got are accurate enough to be useful for the application that you have in hand, okay? If it's accurate enough, then you can stop, but if it's too much of the difference, then you have to keep increasing or decreasing your step size. And as we already observed that the smaller the step size, the higher the accuracy. We know that, right? There's some detailed treatment of error estimate, which is cannot rely on the knowledge of exact solutions, because the exact solution is sometimes, most of the time, is too difficult to find. Then you can find there's some different treatments that you can use in order to manipulate the error estimate, not manipulate, but to smooth out the error or to decrease the error estimate, which is presented in chapter A. In this class, we will, like, Euler's method will be the only numerical method that we will be discussed in this class. But for your projects, you are welcome to pick one or two other numerical methods to study So then you know that there's other different methods that you can use out there. All the methods will have pros and cons, and in order to pick which method to use will depend on the differential equation that you are looking at. All right, here we go. Euler's method, a numerical method that is used in estimating the solution, particular solutions of a initial value problem.